I would like to move on to the next presentation. The next presentation is by Professor Ming Jin from Virginia Tech, Cal alumni and a good friend and associate of mine, who's going to tell us about assured learning-based control for energy systems. Ming, the floor is yours.
All right, thanks, Costas. And thank you, everybody, for having me here. Okay, I'm going to share the screen. Yes. Okay, hello, everybody. I'm Ming, and today I'm very excited to share you about my perspectives on the challenges and opportunities of digital transformation of control in power and energy systems. And now that I look at my slides, I have to confess it's a bit mathematical, but I will try to pop up from now and then and address the big ideas. Okay, so before we start, just a quick overview of what we do. In our research, we are looking ahead of a time when machine learning is increasingly integrated into every fabric of our society, from the built environment to the power grid, from transportation to smart cities. And we want to harness the benefits and understand the potential risks of digital transformation of autonomy. So the overall goal of our research is to develop the trustworthy AI foundations building on techniques of optimization, control, and machine learning. For example, we've been developing algorithms that are able to address uncertainty and even adversarial attacks, scale up data analytics with higher sample efficiency, develop mutual understanding between human and AI, and integrating reinforcement learning in daily operations with assurance of performance. Now, if you look at these are all different aspects of trustworthiness, from robustness, data efficiency, to explainability and adaptivity. And we are going to need all of them for AI to be useful for critical systems. And as we deploy them in the real world, make our power and energy infrastructures more efficient, secure, resilient, human-centric, and sustainable. So in this talk, I'm going to focus on reinforcement learning. And I'm sure that many of us have already heard of the amazing things of reinforcement learning, like famously beating the top master of Go. And in power systems, there are a lot of tasks where reinforcement learning can play a big role. That ranges from managing the distributed energy resources at a scale that has never been dealt with before, or interact with millions of devices on the network, address the ever-changing customer requirements that put stress on the electric assets, and deal with issues like resiliency and cybersecurity. Now, these are all pressing issues and real challenges with big impacts. And the natural question is, like, if RL is so great, right, why not we are seeing enough impacts there? And I think to some extent, we kind of already know the answer, which is that when it comes to RL, by the end of the day, we care about things like performance, adaptations. But as we deploy more and more complex policies like deep neural nets, it's very difficult for us to get any guarantees. On the other hand, like control theory at the very beginning has been dealing with issues like stability and robustness. But it turns out that most of the time we are limiting ourselves to fairly simple policies. So one big theme of this talk is about bridging these two perspectives. We would like to use RL to learn from data, but also use control theory to get guarantees of performance. Another big theme is about bridging the perspectives of optimization and reinforcement learning. Now, optimization is a fundamental pillar to machine learning. We all know that. But this talk is not about optimization for RL, nor will we talk about RL for optimization, like using RL to accelerate an optimization algorithm. But instead, we are going to focus on how we can leverage the synergistic strength of RL, which is adaptation, and optimization modeling, which is interpretability, to come up with a new framework for sequential decision-making. So here's the structure of the talk. I'm going to first talk about safe and assured deep RL, where I'm going to introduce a control theoretic framework towards this direction. And for the second part, I'm going to talk about the recent work that we have been developing called optimization-based implicit RL. So we are going to use optimization as a policy. So the action is implicitly defined by solving the optimization. And I think it's a line of thinking that can lead to very powerful results, but very few people know it. So a big goal of the talk is to make it known to many people. So now let's focus on the first part. Let's jump right into it. So let me first give you a quick 1-minute overview of reinforcement learning. So here we have an environment or a system called a power grid, buildings, smart cities, and we want to control it using a policy. Of course, like we want to do a good job, and we can learn a good policy by interacting with the environment. So the environment can be formulated as a dynamical system. It has a state. The next state is evolving according to this transition dynamics that depends on the current state and action. And also there is a random factor that is going to capture all the random factors in the real world that is not known to us at decision time. For the action, we're going to take a policy output. And this policy could be a neural net. In this case, the policy parameters are the weights of the neural network. But it could be more than that. It could be other things, like in the second part, we'll see it could be a solution to an optimization problem, and in which case, the policy parameters will be the parameters of the optimization model. So the overall goal of RL is to minimize its expected long-term cost that I'm writing here. But let's go a step further by considering constraints on the RL. You can think of constraints are specifications on the trajectories from the system. So the trajectory is just a sequence of input state and action pairs. And the constraint can be encoded in a general nonlinear functions like G of that depends on the trajectory and should be non-positive. And this way we could encode constraints like stability and safety on state action spaces. So the overall goal that we are going to deal with for constraint RL is to find a policy that minimizes the long-term cost while satisfying various constraints. Now, this is a very hard optimization problem over the functional space, and there are different ways of dealing with it. So in the first part, we are going to first focus on imitation learning. But this framework that we are going to talk about is really general, can be developed for other settings of RL that we will see later towards the end of the first part. So what is imitation learning? In a nutshell, imitation learning is that we are given a set of demonstrations from the expert, and our goal is to learn a policy to mimic the demonstrator. The simple setting of imitation learning is called behavior cloning, and it's a simple reduction to supervised learning. So at every state, we are going to make an action that is as close to the demonstrator's action as possible. So we're going to minimize this one-step deviation error. Okay, so the nice thing about this is that it's very simple and data efficient because it reduces to supervised learning. And for example, if you use imitation learning to initialize your policy, you can reduce the exploration for a number of years of data to a few weeks. But there is a caveat, which is that we are dealing with dynamical systems. So even though we have a tiny one-step deviation, it may get accumulated along the way and potentially could lead to catastrophic failures. So under dynamics, we need stability. So even if we start with an undesirable point, we want to revert back to a safe point. That's one requirement. Another requirement is safety. Like in power systems, voltage and frequency are strictly regulated within bounds. So we need our trajectories to stay within a certain regions. So the general question putting them together is like how we can ensure these safety and stability criteria for imitation learning when the policy that we use is a deep neural net. Now, of course, I use deep neural nets because it's a powerful function representation. It's basically you have a bunch of neurons organized into layers, and the input can propagate through various computations to get the output. Now, if you put this neural net into a dynamical system, you can view it as a block diagram. And this would allow us to break down this neural net into a linear part, which is easy, and a nonlinear part. Of course, the linear part is easy to deal with, but so the tricky piece is the nonlinear part that arises from the activation functions like ReLU and sigmoid. So the question is like how we can understand their behaviors. If we could characterize their behaviors, then we have a good control of the behavior of the entire neural net. And it turns out that for many of the activation function, there is a common structure. It's called the sector bounds. For example, if this is my neural net, activation function, it's nonlinear. I can lower bound it with a line and upper bound it with a line. So this nonlinear function lies in between. I can do even better by restricting and pushing up the lower bounds if I know the input lies within a range, which is usually the case. So with this, I know that I'm in business because I can forget about all the nonlinear complexities and just deal with these easy to describe sector bounds. And this is really a powerful approach in robust control, called quadratic constraints, and it can deal with a range of settings that are beyond neural nets. So here is a general framework for safe control and learning. We start with the imitation learning, where the goal is to mimic the demonstrator's actions. And we want to know whether we can use this policy that we design to safely control the system. But analyzing the safety property of this system is hard. So I do a transformation. I replace this neural net with a block diagram that depends on a linear part and a nonlinear part. And I'm gonna bound the nonlinear part with a quadratic constraints. Now, the advantage of this is that now I have a system that's very easy to deal with, and whatever I get from this transformed system, like the safety, it can also be applied to the original system. That's very nice. But then we ask, okay, so what if the neural net is not good enough? What if we cannot certify the stability? What shall we do? Okay, so in a nutshell, we are able to derive a computationally tractable constraint that can be imposed into the learning process for safety and stability. So in this way, we could algorithmically search for the safe policies. So if you think about it, right, so what we are doing is that we are going from analysis, which is to understand what we have, to synthesis, which is to create what we desire. And this is a new paradigm in safe learning and control, and I think it's a big step in the literature. And we have some simple examples on the, here is a small scale commercial aircraft, and we are able to outperform a linear controller like LQR and also ensure the neural net is safe. And we can also generalize this framework to an online setting. And the difference here is that instead of like learning this offline, we can interact with the system in real time by observing from the system. And we are able to come up with a safety set of policies that, as long as we can search the policies within the safety set, we can guarantee that the overall system is safe and stable during the learning and control process. So here is a example in power system for distributed regulation. And here is a model, as you can see, it's nonlinear in general. And we have a bunch of generators on the East Coast. And for each one, we're going to control it with the RL agent. The RL agent is going to search for the parameters. And they can only communicate with each other in a distributed fashion. So the question is, like, where should I search for the parameters in order for us to also ensure safety? Here is a simulation. On the x-axis is the iteration as a proxy of time, and y-axis is the performance. And as you can see, if we just search everywhere without any constraints, there is a point where the system becomes unstable and is unsafe. But if we restrict our search within a set that is guaranteed to be safety, we can see that we can ensure the stability of the system and keep improving without destabilizing the grid. And I think this is a key step towards incorporating RL in safety critical systems. And recently, we are also working along the directions of how we can learn the neural net and the general specifications, like from this framework that we have proposed, beyond adversarial robustness, beyond safety, so that it can be applied to other settings as well. And this we are still not there yet. We are working towards it, but we are very excited about this direction. Here is a quick reference. So that's about the first part. Now for the second part, I'm gonna talk about this optimization implicit RL. So let me start with a motivating example. For folks in California, you might have already heard of this or seen this famous stock that has been bugging California ISO for the several years in the past, and is believed to be one of the greatest challenge in managing solar generations for the decade to come. It's called the duck curve, and it's typified by the low demand during the day, when folks in California with a solar PV would use the energy directly from there, and from the operator's perspective, it looks like a drop in demand. But when the sun goes down, the demand peaks comes along, and the power demand on the system rockets up by more than 10,000 megawatts in a very short period of time. And you could imagine that this poses a tremendous challenge for the current power infrastructures. And it also substantially reduced the environmental and economic benefits of solar generation. So how can we deal with this issue? One of the most promising approaches to use storage, because the storage can effectively shift this excess generation from the middle of the day to later in the evening when demand peaks. So one of the fundamental problems in energy is storage dispatch. So how we can turn on and off this storage during the day in order to flatten the curve. And this essentially is a planning problem, because we need to anticipate the future demand and future solar generation in order to make a decision at the present. So when it comes to planning, the golden standard is the optimization. And I think it's a language that the power industry is also starting to embrace. Well, it's very easy to formulate this as an optimization problem, where we would just minimize some cost functions like the total electricity cost or the peak demand subject to constraints like power balance, supply always equal to demand, or various technology constraints like the maximum charging or discharging rates for the storage. So this optimization is easy to formulate and often easy to solve, because it also often turns out to be a linear program, quadratic programs, that there are solvers for it. And once we get an action, we can implement in the real world. We could do even more fancy approach like rolling horizon, where we solve this optimization every hour, like the way we do in model predictive control. Now, as you can imagine, this is an approach that is widely adopted in practice for various problems in power and energy. And there are very good reasons for it. For example, the first one is the optimization model is interpretable, right? So the energy modeling has been going on for decades, and we have a clear understanding of what we put into the optimization model. And that's crucial because we can then trust these policies in the real world. And it's also easy for us to enforce constraints. And because often the time we are ending up with a convex program or even mixed integer programs, we have reliable solvers to solve it. But there are also some issues that we have to deal with. We have to live with it for the current approach. The first one is how we can manage uncertainty. Well, we can certainly make predictions and use the predictions in our optimization model, but prediction ultimately comes with errors. For example, if you think about this very toy problem, like I want to find the cheapest product. It wouldn't change my decision if I overpredict the price of the most expensive product. Nothing would change. But if I underpredict the most expensive product, then there will be a large decision error. And that's the issue here. We have errors in predictions, And this error would be compounding in the decision-making process in a non-trivial way. So a small error could potentially lead to a huge error in the decision. There are also issues like model mismatch, right? Maybe the true model is too complicated, we have to make approximation, or maybe we just don't know the true model specs. So a lot of these are just estimations. And also the real world is changing. Nothing fixed, how can we adapt to the real-time conditions? So then we say like, okay, so let's take the standard approach of doing optimization and let's make it adaptive. So we are gonna put into place an RL agent that is going to tune the predictors and optimization programs based on the data that we see. So if you think about this, this is exactly RL. But the key difference here, the key feature here is that instead of using a parametric functions or non-parametric functions like neural net or Gaussian process, here we are using the solution of an optimization problem. So the action is implicitly defined by solving this optimization program. And the tuning of the parameter has also implicit influence on the decision-making process because of it. And because of this, we call this implicit RL just to highlight this difference. And if you think about, like, to put it more generally, the way we have been teaching like our students in engineering school is that one rule of thumb is divide and conquer. So if I want to have the best decisions, we'd better have the best prediction, best optimization. Putting them together, we would hope that we have the best decision. But we are missing a very important factor in the real world, which is that we often face constraints. So we may never have perfect prediction or perfect optimization. Somewhere in the process, we are gonna make compromise because of the constraints in information or constraints in computation. And often the time, those compromise will turn out to be the weakest link of our pipeline that could eventually break the system. So over here, we're not doing divide and conquer, but we are really adopting a pipeline approach. Right? We're focused on this pipeline, and then we say, let's live with the imperfections of each individual models, but let's try to achieve an overall good performance. So this RL agent is not trying to match the predictions or match the optimization models because there may be no ground truth, but it's just trying to make a decision overall that is good for the performance. So that's the framework, that's the idea. And if you're really interested in like how we do it, I can walk you through this very quickly. Let me check the time. So, okay, so we're going to start with the performance goal. And here is written as to minimize the sum of expected cost. It's a very hard problem because we are going to search over functional spaces. So what Bellman tells us almost like 70 years ago is that we can break this sum into a value that depends on the current action and the expected value for the future that this action entails. And this is direct look-ahead model, but it's still hard because here we have a two-stage optimization. It's by no means easy. And also inside, we need to evaluate this expectation that depends on things like transition dynamics, which we may not know. So we're gonna kill two birds with one stone by doing a deterministic approximation for the future. So instead of doing the original objective minimization, we are gonna use a surrogate model. Because overall, and we are gonna make some, we're gonna tune the surrogate model to compensate for the approximation errors that we make in this deterministic approximation. And here exactly is the place that we are gonna plug in the predictions. So then, if we solve this surrogate model, the action can be applied to the real world system, and that's our policy. So we can tune the parameters in the surrogate model based on what we have observed in the real world. We are not assuming that we know about the transition dynamics, so it's not possible to differentiate through this optimization. Instead, we only get to observe noisy cost samples. So this optimization problem, again, is easy to write, but very hard to solve because it's a non-convex in general. So how do we go about it? So we came up with this approach called zeroth order search with guidance. And it's really inspired by what we do in practice. So we're going to start with a prior distribution, which is determined by the domain knowledge, because often the optimization model is quite interpretable. We have good understanding of how we set the parameters. And from the distribution, we're going to sample a bunch of candidates. For each candidate, we'll evaluate it on our real system and get costs. So we'll get a bunch of costs, and here we're going to apply the guidance. The guidance can be a general functions that depend on all the costs. For example, I can find the best few candidates and average them, mix it with my current candidate. That's one guidance, but we could do even more general things like those based on the insights from the domain experts. So using this way, we could lead the search with these guidance functions, and then we are going to generate the new distributions with the guidance. For the next iteration, we're going to mix them up and weight them based on their performance in the current iterate. So the best candidate gets sampled more often, but also with some randomness because we are exploring the space. We're able to come up with some theoretical guarantees, which I'm not going to go into details. So basically, under some regularity conditions, we can assure that the distribution of the solution can converge to the stationary optimal distribution and at a geometric rate. The rate depends on the guidance factor, noise variance, etc. But what I would like to highlight here is, first is the contributions. So here we are able to design an implicit RL framework that can adapt the optimization program for sequential decision making. And in our paper, we also extend this to multi-agent distributed control settings. And this zero-order search with guidance has theoretical guarantees of global convergence. It's a non-convex optimization, but it has global convergence. And we are later going to show some performance it results that this technique can overperform like some existing RL methods in some very interesting problems. Just to highlight some conceptually related work, Benjio in 1997 was the first to came up with the idea of learn a model for the downstream task. Dante and Amos Cotter in 2017 proposed to use implicit differentiation to solve a stochastic optimization problem. And in operations research community, there is a very nice line of work called Smart Predict, Then Optimize, which shares a similar philosophy. But so far, like all of these works are focused on single state decision making. And recently, Boy's group at Stanford is able to come up with a convex optimization-based policy for control, but they assume the system knowledge is known in order for them to derive the implicit differentiation. In the control community, learning MPC led by Borelli at Berkeley is closely related. And I want to point out this amazing book by Powell on RL and stochastic optimization, which really provides a very nice and unified view of how we can address these type of problems. And there are, of course, other keywords that I'm not going to read it here, like cross-entropy, evolutionary algorithms that are related to the algorithmic design. But what really gets me excited is really like, I think this approach can become a vehicle for RL to the domain to have an impact in domains where traditionally are dominated by optimization approaches. And here we're just gonna see like a list of challenges that this approach can potentially address. And they come from this paper at this bottom. The first challenge is to learn on live systems from limited samples. And of course, like I could get by without any samples. That's just purely optimization-based approach. Of course, we want to do better, but this also means that our approach is backward compatible. And I think that's very crucial when it comes to practice. And the second challenge is that we could, the second thing is that we could act in a high dimensional state and action spaces because of the reliable solvers available to us. And we are also able to address the system-wide requirements by encoding them as constraints and use distributed optimization to interact with partially observed systems and adapt with data. And also we could learn from multiple objectives the way that we deal with in multi-objective optimization. And what's really important is that the overall approach is very interpretable. It's much easier to inspect into an optimization model than look into a black box like neural net. So City-Learn is the test bed that we have tested the algorithm. It's a challenge organized by folks in UT Austin and UC Boulder. It's basically the energy storage coordination problem, but at a larger scale. And we're gonna see, how we can address this challenge. And actually, this is the challenge that deal with a range of the real world RL issues that I have in the previous slide. So for example, in this challenge, there is no training period. It's only an episode with 4 years of evaluation. So the control policy will be evaluated the moment it's put into practice. And also we need to control group of buildings with continuous state and actions. And the problem comes with balancing equations and technology constraints. And it's also a decentralized control setting where the buildings cannot communicate with each other. And we need to deal with seasonal variations in loads and solar generations. And there's no access to model. So we have to learn from data. And there are different performance metrics that I'm listing here. So I'm not going to read them, but they are basically measuring energy flexibility, efficiency, and things like carbon emissions. And there is also a baseline called rule-based controller, RBC. And essentially, if we get a cost ratio that's less than 1, then we are doing better than RBC. Otherwise, we are doing worse. Here are just 2 metrics that we plot. It's similar for the other metrics. I'm not showing them all. And we are comparing with RL method like Software Actor Critic and Melissa, which is state of the art. And you see that here, our method is the best in terms of the cost metrics. We could also look into the learning performance. Here on the x-axis, the month, y-axis, the cost. We start with optimization initialized. So it's not as good as RBC. The reason is straightforward, is that we are dealing with a model that's wrong. So even though we solve for optimality, we are dealing with the wrong objective. And that's why it's worse. But as we adapt, we quickly get better than the RBC. And we can also inspect the model parameters. Over here, the parameters we learn are the virtual electricity prices. It's not the actual price that we need to pay, but it's, if we put a high price, it's a virtual price that if we set it high for a particular hour, then the model will be cautious of using more electricity. And here, it looks like we are learning something. So we dig into the data, and turns out is that for this particular building, it tends to overpredict the demand later in the day. So it ends up charging more than it needs in the morning. And that leads to unexpected demand peaks at the very beginning. So by adjusting this, increasing these virtual prices in the morning, we are able to sort of regulate the load curves. And I think that's kind of revelatory. And so far, like we've been talking about 2 different policies, neural net and optimization based. And when it comes to power systems, there are a variety of problems that can be separated by time scales, literally from microseconds to years. And when we design the policy, it's really a constraint we need to consider. And by the way, this is a very nice graph from Sasha. And this is the best graph. I couldn't find anything better. Okay. And another thing we need to consider is the decision-making layers is the only thing that we've been focusing on. But when it comes to the real world, there are also other complicated processes like sensing actuation, networking communication, and data processing. And what we do in the decision-making layer should really account for all the things that happen before it. right? So for example, we've been considering like how we can deal with communication issues in our decision making and how we can deal with data quality issues in downstream tasks. And when it comes to like real world, making things happen, we have to work with industry closely. I think that's one of the major themes of this talk, this workshop is the cross-pollination of ideas. And I'm glad that we also have folks from C3 after this talk, Varun and Bird, who will be talking about the C3 aspects. And when it comes to getting things done, we really need like software frameworks like C3 AI Suite that's gonna cut across the layers and really make things happen. So in this talk, I have a talk about learning-based control and how we can get trust for them. And ultimately, these methods are going to make their way into the real world. So I think it behooves us to kind of start addressing these issues before they actually occur. Finally, I would like to acknowledge all my amazing collaborators who have helped this project in different ways. I'm very grateful, and here are some references that I put in here. I'd be happy to answer any questions. Thank you.
Thank you, Ming, for an excellent presentation. Quite refreshing. Glad you're making so much progress since last time we talked. I do want to start with a general question. As you probably guess, my question always has to do with link to actual data. And you use distributions, you use estimations, and I wonder, is there a real barrier in applying these things to an actual problem? And is this barrier related to data availability or interpretation?
Okay, so I think when it comes to getting this really like into the real world, the implicit optimization that I talk about is already addressing some of the barriers like interpretability and the issues with predictions. But of course, as I said, there is a pipeline. And so far, like decision-making layer for the implicit optimization is also kind of restricted to only consider what happens within the layer. But what if like there are really like bad data or attacks on different layers and there are networking issues that cause delays, and all of these issues needs to be addressed in a principled manner. So I think these could be the barriers when it comes to designing the policies.
Thank you, Ming.